Okay, I'm going to take the example that I just discussed in some detail. I'm going to put it into a general setting. I'm going to show you how you ask the questions that I asked in that general setting. I'm going to derive the more accurate, more rigorous equation for the nudging that I showed you. And then I'll talk about using it in neurobiological examples, using data from Margolius's laboratory. Then we'll probably have a break again. And then I'll talk about how you apply this to what is in the books on machine learning. So where are we? All right. So I started to outline other interesting nonlinear systems. Suppose I had received the atmosphere for a New Year's present. That's a little bit bigger nonlinear problem than just the transistor. I would have done exactly the same thing, except it's a little difficult to perform the experiments in any old way that you want. The forcing of the atmosphere is given to you, but I think we know something about it. One is dealing with climate issues, and in particular, the way human-injected greenhouse gases can affect that climate. We have to know something about the future of the way that the atmosphere is constructed. But if you give me the atmosphere for today and for the next few months, the problem is essentially the same. The number of variables is much larger than 3. It's much larger than 10 to the 3. And therefore, the actual issues that you have to face are more complicated in practice. But I want to give you the framework in which I suggest that you answer the issues. If you're dealing with lakes, there was somebody here yesterday who was talking about limnology. I think he's not here today. If you're dealing with oceans, well, that's just the other half of the Earth system. It has different timescales and different dynamics. But you might want to connect that with your first problem, the atmosphere, if you really want to discuss the Earth. If you're talking about biological cells or whatever is your system of interest, if it's linear, you don't need the machinery that I'm going to put up here. You can do it exactly following the work from 1960, which I remind you is almost 60 years ago. There's got to be some improvements in 60 years, both from conceptual and computational technology. At the bottom, I say again, you need the following quantities. You need good data. In the context of machine learning, I'm going to call that curated data, which means that you actually have some idea of what problem you're trying to solve, and you have some data about it. You need a model, and a priori you're not told what the model is, but if I, in fact, gave you the atmosphere for your New Year's present, you wouldn't be crazy to think about fluid dynamics as a good start. As I said, the boundary conditions are complicated. All sorts of other things are complicated and need to be parameterized. You have some idea of what the model is. And finally, mostly what we're really talking about is a way to minimize the distance between the data and the model variables, and that goes under the name of data assimilation. All right, so now I'm going to put this in a general context, and here's what it is. Whoops. Okay, so here's the picture. I have a window of time from some time t0 to some time t final. And during that window, I observe data, which I'm now going to be calling y. I'm sorry about the flip in notation, but it was actually Eugenia who told me I should change my notation a few years ago, and I did. No, you gave me very strict orders, and of course I obeyed. Sorry. No, you were right, because this is now consistent with what other people use. All right, I make measurements in this window whenever I can. I don't know what the instruments are. I'm not trying to dictate that. And also at every one of these times tau, I make more than one measurement. I'm going to call that number L. Make all those measurements. I put them aside in a nice storage area. That's my library. I'll come back to my library. I don't have to touch it again. Now I make a model. I make a model based on the physics, the biology, the biophysics, whatever it is that you know that leads you to think that the outputs of the model underlie your observations. I do not know a button in MATLAB or any other program that says make model. So you are all still employed. And that's the hard part, in my opinion, and the interesting part. And then I need a way of starting the model here, moving it forward to the first measurement time, modifying something about the output of the model, then moving it along in however many steps I think I need to accurately represent the solution of the model, and connect it with the next observation. And then do it again, and do it again, until I've finished my measurement time and I'm done. I want to estimate at this final time the state variables of the model, temperatures, pressures, voltages, currents, whatever, and then use the model to predict forward to validate the model. If the model has d dimensions at every time, I'm going to call the model x, then typically I'm measuring at the taus many fewer dimensions than d. In the example I gave, d was 3. I measured 1. In the case of really complicated systems, say, for example, for a neuron, you may have state variables that control the permeability of cells to sodium and potassium and calcium and chlorine and whatever else. You may have internal dynamics. And what you can measure typically in a straightforward and accurate way is the response to a current put into the neuron that causes the currents flow and the neuron to do its activity. And you can measure the voltage across the membrane. So you may have 10 or 12 dynamical variables and one measurement. So there are two questions. How frequently do you make the measurements? What's the spacing between the taus? And at each tau, how many measurements do you make? And those are important questions, and I'm not going to address them in detail today, but I'm going to assume that we did pretty well. This problem is a stochastic problem because we don't know the distribution of the state of the system at the initial time. So we can't just take the equations of motion that we somehow derived and move it forward with high accuracy until we know the distribution when we start out. That probability distribution, Sebastian properly called the prior. If you're a physicist, you call it the initial conditions. Prior sounds mysterious, but anybody who ever solved a differential equation knows you have to tell it where to start. You then have to move it forward, and in every time you make a measurement, that measurement has errors. And this is all you know. So what I want to do is calculate the joint probability distribution of all of the measurements made in my allowed time, conditioned on all of the states of the system in my time, conditioned on the measurements that I made. If I can calculate or give a representation of this conditional probability, then I will have a framework in which to answer the question, how do I transfer the information that's contained in the measurements into the model? That's our goal. So here's the picture. So noisy measurements, errors in the model. Once I've done all that, I take the state of the model at the end of the time you allowed me to make the measurements, and I predict. And that's the critical aspect of validating your choice of the model, actually also combined with your ability to transfer the information in the measurements themselves. Here's simply another picture of what I just showed you. You can think of this as the measurements as a transmitter. They're transmitting you information about the thing or system you're observing. If they transmit it over a radio link, which we call the communication between the measurements and you want to tune the aspects of your receiver so that it receives as much information possible as you can get. The transmitter has many, many fewer degrees of freedom than your radio. So you have some hope of adjusting the output of your radio where it matches the measurements in the transition so that they are the same. This should really be approximately the same because there are errors in your measurements. And so what you can get is the same within an error ball somehow in the space of measurements. This has a fancy name. It's called generalized synchronization of the transmitter and receiver. And it was studied in the world of nonlinear dynamics 20 years ago. Doesn't mean it was fully understood, but a lot is known about it. If you want to have a look at that literature, which I'm not going to discuss or refer you to, you'll find it helps. I found it helped understand the process that you're undergoing here. OK, I think I've said all this. And I think I have said all this as well. All right. Turns out there's a useful and very nice connection between the probability distribution at some time, given measurements up to that time, and the probability distribution one time earlier, given measurements up to that one time earlier, conditioned, it's the probability of the state one time earlier given measurements up to one time earlier. I'm going to show you that recursion relation. Once I know how to relate the distribution at this time to the distribution at one time earlier, I can then, by simply marching back from the end of your measurement window to the beginning, give you a general representation of the probability distribution as a whole. I need two things. I need the definition of a conditional probability distribution. Some people attribute that to Mr. Bayes, but I suspect that other people invented it as well. He had a nice interpretation. But all I need is the definition of a conditional probability distribution. And given that my model has errors, I have to know how, if I know something, a distribution of the state at this time, what to expect probabilistically as a distribution, not as a sharp delta function, but as a distribution in outcomes of what the state will look like sometime later. That is precisely related to what Sebastian talked about as properties of stochastic differential equations. If what he called Q goes to 0 or infinity, I forgot which limit, you had a Q which was related to your fluctuations. If those fluctuations go to 0, if you know where you are in state space, x space at time t, you know exactly where you will be at time t plus 1. If you have errors that you represent by these fluctuations, you only have a probability distribution of where you will go. When I am finished identifying where to put that information, you will see it as exactly what Sebastian was talking about yesterday. And I appreciate your setting the stage for all that.